Welcome to my online course in linear algebra for undergraduate mathematics. Today's topic of discussion is eigenvalue and eigenvector, eigenspace. First, we will discuss what is eigenvalue and eigenvector. Let T from V to V be a linear operator where V is a vector space over the field F. Then a scalar lambda belongs to F is said to be eigenvalue, also known as characteristic value of T, if there exists a non-zero vector V belongs to V such that T of V is equal to lambda V. Here V is called my eigenvector or characteristic vector corresponding to eigenvalue lambda. First, eigenspace. Let T from V to V be a linear operator and lambda be an eigenvalue of T. Then the set of eigenvector corresponding to eigenvalue lambda denoted by V lambda is a subspace of V. Here, V lambda is the collection of all vectors of V which satisfies the condition T of V equal to lambda V. That is, V is the set of all eigenvector. V lambda is the set of all eigenvector corresponding to the eigenvalue lambda. Since 0 belongs to V, T of 0 is equal to 0. T of 0 is equal to 0 and it can be written as lambda 0. Therefore, 0 belongs to V lambda and V lambda is my non-empty. Let B1, B2 belongs to V lambda and alpha 1, alpha 2 belongs to F. As B1, B2 belongs to V lambda, T of B1 is equal to lambda B1, T of B2 is equal to lambda B2. We are going to show that V lambda is my subspace. That is, we are going to show the necessary and sufficient condition for a non-empty subset to be a vector space. That is, if x1, x2 belongs to a subset of vector space, and alpha beta be any scalars, then alpha x plus beta y belongs to the subset. That is, here we have considered B1, B2 belongs to V lambda and alpha 1, alpha 2 belongs to the scalar. So we are going to show that alpha 1 B1 plus alpha 2 B2 belongs to V lambda. For that, we consider T image of alpha 1 B1 plus alpha 2 B2 which is equal to alpha 1 T B1 plus alpha 2 B T of B2. Since T is linear combination, T is linear operator, we can write this one. Alpha 1 T of B1 plus alpha 2 T of B2. Put the value of T of B1, it is equal to alpha 1 lambda B1 plus alpha 2 lambda B2. Take lambda common, it will be alpha 1 B1 plus alpha 2 B2. That is, T of this element is equal to lambda of that, lambda of the element. Therefore, this element belongs to the set of eigenvector V lambda. Hence, V lambda is my subspace. This is a special subspace known as eigenspace associated with the eigenvalue lambda of T. Next, example on eigenvalue, eigenvector and eigenspace. First example, let T from R2 to R2 be a linear operator defined by Txy is equal to x plus y, x plus y. Find the eigenvalue and eigenvector of the linear operator T. Generally, we find out the eigenvalue and eigenvector by using characteristic polynomial and characteristic equation by finding the matrix representation of the linear operator. But here we will find eigenvalue, eigenvector by inspection, by using intuition. We will discuss characteristic polynomial and characteristic equation in our next lecture. Here we are going to find eigenvalue and eigenvector by using inspection. By inspection, so take T of minus 1 and 1, that is, in place of x we will put minus 1, in place of y we will put 1, then this value will become 0 0, that can be written as 0 minus 1 1. So it will be in the form T of b equal to Cp, that is, here C is my 0 and vector is minus 1, 1. That is 0 is my eigenvalue and minus 1, 1 is my eigenvector corresponding to eigenvalue 0. Again take the vector x equal to 1, y equal to 1. Then it will be 2, 2. So take 2 common. It will be 1, 1. So here 2 is my eigenvalue and 1, 1 is my eigenvector. Next one, let T from R2 to R2 be a linear operator defined by Txy is equal to x0. Find the eigenvalue, eigenvector and eigenspace of the linear operator T. If C belongs to R is an eigenvalue of T, then there exists a non-zero vector xy belongs to R2 such that T of xy is equal to Cxy. By definition of linear operator Txy, it is equal to x0 is equal to Cxy. That is x0 is equal to Cxy. This can be written in the form Cy. We bring C inside the bracket, then equate the left hand side and right hand side. This can be written as x equal to Cx and 0 equal to Cy, which can again further reduce as x c minus 1 equal to 0 Cy. Now x c minus 1 equal to 0. Take this. If x is equal to 0, then y must not equal to 0. Otherwise, this vector will be 0 vector, and it is 0 vector. In the definition of eigenvector, the vector must be non-zero. Here, if y is not equal to 0, then from the equation cy equal to 0, we get c is equal to 0. If c is equal to 0, x is 0, and y is non-zero, this is my eigenvector. 0, y is eigenvector. In particular, if we take y equal to 1, then 0, 1 is my eigenvector corresponding to eigenvalue 0. That is, if I take the image of 0, 1, then by definition of the linear operator, here it is 0, it is 1, so it will be 0, 0. That is, t of 0, 1 will be my 0, 0. That can be written as 0 into 0, 1. So 0 is my eigenvalue of t. Next, if c is not equal to 0, then this equation cy equal to 0 implies y is equal to 0 and c is equal to 1. By the definition of this vector, that means x0 is my eigenvector corresponding to the eigenvalue c equal to 1. In particular, if I take x equal to 1, then t of 1, 0 is my eigenvector. It can be equal to, by definition of linear operator, here it is 1, 0, so it is 1, 0. And it can be written as 1 into 1 into 1, 0. That means 1, 0 is my eigenvector of t corresponding to eigenvalue 1. Now we are going to find out eigenspace of t associated with eigenvalue 1. So W1 set of all vector in R2 such that t of xy is equal to xy. Now this is xy. By using the definition of linear operator, this is x0 is equal to xy. Now here from here we get y equal to 0. That means my x-axis, this is y equal to 0. So this means x0 is here eigenspace corresponding to eigenvalue 1 consisting of all element of the form this, that is my x-axis. Next is the theorem. Let lambda 1, lambda 2, lambda n be n distinct eigenvalue of a linear operator t on V if b1, b2, bn be n non-zero eigenvector corresponding to lambda 1, lambda 2, lambda n respectively, then b1, b2 are linearly independent set. Given t of b1 equal to lambda 1, b1 as lambda 1, lambda 2, lambda n are n distinct eigenvalue of the linear operator. So t of b1 is equal to lambda 1, b1, t of b2 is equal to lambda 2, b2, up to t of bn which is equal to lambda n bn. We shall show that this b1, b2 up to bn are linearly independent set. We shall prove this theorem by induction on n. If n is equal to n, the result is true, as non-zero singleton subset of a V is always linearly independent. If I take n equal to 1, T of B1 is equal to lambda 1 B1. If I equate this 0, since non-zero subset of a vector space is always linearly independent, so this result is true when I take n is equal to 1. If I equate this equal to 0, then either this equal to 0 or this equal to 0, as this is non-zero, so this must be 0, so this is linearly independent. Now we shall show that the result is true for all n. For that we consider result is whole for all value of n, all value less than n. Now we are going to show that the result holds for n. For that we have considered alpha scalars alpha 1, alpha 2, dot 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 alpha n, such that linear combination of the scalars and eigenvectors b1 b2 up to bn is equal to 0. That is alpha 1 b1 plus alpha 2 b2 plus dot 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 alpha n bn is equal to 0. Now take the image of this equation in both sides, we will get this one. Using the property of linear operator, we can write this in this form. Okay, then put the value of T of b1, T of b2, T of bn from here. We will get this equation, that is alpha 1 lambda 1 b1 up to alpha n lambda n bn. Put this equation 2. Now multiply the equation 1 by lambda n and subtract it from equation 2. Multiply this equation by lambda n, lambda n, lambda n and subtract it by 2. Here it will be alpha 1 and b1 is common in both the equation. Alpha 1 and b1 is common. Here it is lambda n, here it is lambda 1. Subtract lambda n from lambda 1, I will get this term. Similarly, in the second term, I will get alpha 2, lambda 2 minus lambda n bn goes up to here last term. It is alpha n lambda n bn. Here if I multiply the first equation by lambda n, it will be alpha n lambda n bn. So last term cancel out. The term in the equation 1, the term before the last term will be alpha n minus 1 bn minus 1 into lambda n, and the term before here, before the last term in the equation 2 is alpha n minus 1 lambda n minus 1 b n minus 1. So alpha n minus 1 and b n minus 1 is taken common. The term inside the bracket is lambda n minus 1 minus lambda n. In the beginning, in the induction hypothesis, we consider the result hold for all value less than n. So these vectors, this set of vector b1, b2 up to bn minus 1 are linearly independent. That means this coefficient are 0. That is alpha 1 lambda 1 minus lambda n is equal to 0 up to alpha n minus 1 lambda n minus 1 minus lambda n is 0. This is lambda n suffix n. Since lambda 1, lambda 2 up to lambda n are n distinct eigenvalue of the linear operator t, so these differences lambda 1 minus lambda n, lambda 2 minus lambda n up to lambda n minus 1 lambda n are not 0. Only option is alpha 1 is 0, alpha 2 is 0 up to alpha n minus 1 is 0. Now from equation 1, all this term before all this term up to alpha n minus up to last term, except last term, all the preceding term are 0. Except last term, all the preceding term are 0. So last term is alpha n, bn is equal to 0. As bn is a non-zero vector, b1, b2 up to bn are non-zero vector, the only option is scalar is 0. That is alpha n is 0. Here we have got alpha 1 is 0, alpha 2 is 0 up to alpha n minus 1 is 0. Here I have got alpha n is 0. Therefore, the set of vector in equation 1, b1, b2 dot 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 bn are linearly independent. Hence the theorem. These are your home assignment. Try to solve this home assignment. In case of any doubt, any question, any difficulty, you can ask me. Do not wait for the end of the unit for doubt clearing session. You can ask me your doubt problem at any time. With that, I would like to conclude. Thank you. Remaining will be in the next class.